So there was some network issue. So we were discussing the decoders. The decoders are the combinational circuit which are used for the logical switching operations. This is a kind of switch, and how it works. Let us discuss about in detail. A decoder is a combinational circuit. It accepts a set of inputs that represents a binary number and activates only the output corresponding to the input number. So whatever is the input combination, according to that, it a single output will be activated, and at that time all other outputs remain inactive. So it will depend upon the which type of logic we are using. If we are using logic high, then 1 will be considered as active case and 0 will be considered as inactive case. If we are using the negative logic, then 0 will be considered as active case and 1 will be considered as inactive case. So now in the figure we will show that in a decoder in general it has n number of inputs and m number of outputs, and the relation between m and n is that m equals to 2 raised to the power n, because with the n input combination we have 2 raised to the power n possible combinations, and for each of these input combination only one output will be high, and high is considered as active and all other outputs are low. Some decoders have one or more inputs which is known as enable, and that are used to control the operation of the decoder. So enable is may be considered as chip enable. Whenever enable is active, it is said that that particular IC will be active or the IC will work, otherwise the IC will not work. So this is the another input. It may or may not be present in any decoder, and and it is rather extra with the n number of inputs. So this is a kind of block diagram of a decoder. It has n number of inputs from A0, A1, A2 up to An minus 1, like this. We have denoted output by B. So it has m number of outputs and only one output is high for each input combination. When we'll move to the truth table, then it will be much more clear about what is the relation between input and the output. Now, a code of n bit can represent 2 raised to the power n decoded outputs. So one output is true at a time. So this is a block diagram, n number of inputs. We can have some enable inputs, which is desirable. Whenever which is desirable, it is used, otherwise it is not used. And we have 2 raised to the power n possible output combination. So decoder is named as n is to 2 raised to the power n. So suppose if I say it is, if the input n is 2, then decoder is said as 2 is to 4 decoder or 2 is to 4 line decoder. So this is the name of the decoder, how it is called, n is to 2 raised to the power n decoder. This will be the size where n will be the number of inputs and 2 raised to the power n will be the number of outputs. Now let us first discuss about 2 is to 4 decoder. So it means, as clear from the name, that the number of input will be 2 and the number of outputs will be 4. So the block diagram of 2 is to 4 decoder we are going to discuss. Suppose it has 2 input and I have named them A and B. So the A and B are the 2 inputs. Number of possible input combinations are 2 raised to the power 2 equals to 4. So there will be 4 outputs. And we have named 4 outputs as D0, D1, D2 and D3. So therefore the 2 is to 4 decoder has 2 inputs which are named as A and B. It has 4 outputs. which are named as D0, D1, D2 and D3. Now come to the block diagram and truth table of the decoder. So you can see the truth table. Here are two inputs, A and B, four possible combinations 0, 0, 0, 1, 1, 0 and 1, 1. And these are the four outputs, and you can see directly that at one time only one output is active, that is 1. So for 0, 0, D0 is 1, for 0, 1, D1 is 1, for 1, 0, D2 is 1, for 1, 1, D3 is 1. So we can see that for any input combination only one input output is 1 and all rest of three are zeros. So this is the way how the truth table looks like of a 2:4 decoder. So here is the block diagram of 2:4 decoder. A, B, two inputs. D0, D1, D2 and D3 are four outputs. Now let us discuss how the internal construction of decoder is. The Boolean expression we can find out directly from the truth table. You can see here from here, D0 is 1 when both A and B are 0, 0. So D0 equals to A bar, B bar. D1 is 1 when the input combination is 0, 1. That means A bar, B. D2 is 1 when the input combination is 1, 0. That is A, B bar. And for D3, it is A and B. So directly we can write the expressions like D0 is A bar B bar, D1 is A bar B, D2 is A B bar and D3 is AB, and we can directly construct the internal structure of the 2:4 decoder with the help of AND gates. So here is the logic. We have a line A, input A, we have complemented it with the inverter that will produce A bar. We have input B, we have a complemented line that is B bar. Now the first is D0, D0 is A bar, B bar. So A bar comes from here, B bar comes from here. Then A bar and B, A, B bar, A and B. So this is the structure of a 2:4 decoder, how it is constructed. So whenever you are going to construct or discuss the decoders, first of all write the truth table of that particular decoder, and keep in mind that at any time only one output will be 1 and rest of the outputs will be 0. Next is 3:8 line decoder, or we can say binary to octal decoder, because 8 is nothing but octal. So 3:8 line decoder, how it works. Again, we have three inputs. So we name it as A, B and C are the three inputs. With the three inputs, we have 2 raised to power 3, that is 8 output. And I have named them 8 outputs as D0, D1, D2, D3, D4, D5, D6 and D7. So these are the 8 outputs. Again, in the truth table, only one output will be 1 and rest of the output will be 0. This will be the block diagram of the 3:8 decoder, 3 inputs, 8 outputs. Inputs are ABC. Outputs are ranging from D0 to D7. Let us write the truth table. So with 3 inputs, we have 8 combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. And you can see again in the output line that at a one time only one output is 1. For the 0, 0, 0, that is 0, D0 is 1, for 0, 0, 1, D1, 0, 1, 0, D2, 0, 1, 1 is D3, 1, 0, 0 is D4, 1, 0, 1 is D5, 1, 1, 0 is D6 and 1, 1, 1 is D7. So you can say the subscript 0, 1, 2, 3 is nothing but that is the equivalent binary value of the input. And again, from the truth table, we can directly reduce or derive the expression for the outputs from here. D0 is 1 at 0, 0, 0. That means A bar, B bar, C bar. For D1, it is 0, 0, 1. That is A bar, B bar, C. For D2, D2 is 1 at 0, 1, 0. That is A bar, B, C bar. For D3, it is 0, 1, 1. That is A bar, B, C. D4, it is 1, 0, 0. That is A, B bar, C bar. D5, it is 1, 0, 1. That is A, B bar, C, A, C. D6 is 1, 1, 0. That is A, B, C bar. And D7 is 1, 1, 1. That is A, B, C. Now, after getting the value or the Boolean expression for the outputs ranging from D0 to D7, we can directly construct the logic diagram, and the logic diagram seems to be like this. So again, we have three inputs A, B, C, which are true. We have complemented on A, B, C with the help of three different inverters. So it will produce A bar, B bar and C bar, and in the same way as we have constructed 2:4 decoder, we have tried here to construct a 3:8 decoder. Now, what's the purpose of an enable? So here we have tried a 2:4 line decoder with an enable input. So here I have used a negative logic, that is 0 will be considered as active and 1 will be considered as inactive. So whenever enable is 1, whatever is the output, whatever is the input combination that I have traced cross, that is don't care. So whenever enable is inactive, I don't care about input and the output will be inactive. Inactive means 0. So this is the way. If the enable is 1, we don't care about the input, output will be inactive. Whenever enable is 0 and for 0, 0, D0 will be active, that is 0. For 0, 1, D1 will be active. For 1, 0, D2 will be active, and for 1, 1, D3 will be active. So this is the way how the enable works. So enable is here used only to select the particular chip or particular IC. Whenever enable is inactive, whatever is the input combination, your IC will not work. So we can find out here the circuit diagram. So here is the circuit diagram. A bar, B bar, AND gate, and we have used, because here 0 is the active, we have used it here the NOT gate. Enable is like this. So this is how an enable is connected. Whenever enable is 1, so this enable will be 1. Output of the NOT gate will be 0. 0 will fed to the NAND gate, and for the NAND gate, if any input is 0, output will always be 1. So at the same moment, whenever enable is 1, the output of all three gates will be 1. So this is the way how an enable pin works in a decoder. The expansion of decoders, we can construct a larger decoder with the help of small decoder. If you have seen RAM in your computer, if you pull it out, you will find out if you are using a 4 GB of RAM, then it may be possible that there are some slots or some ICs of 512 MB. So making a 512 MB RAM will make a 1 GB RAM, and in the same way, to get 4 GB of RAM, you require 8 512 MB RAMs. So when you combine a 512 MB RAM, it will construct a 4 GB of RAM. So whenever you pull out a RAM from your system, you will find that there are small RAMs and they are arranged in such a way that a larger RAM or a larger memory is obtained. So this is the way, in the same manner, we can extend our decoder, or we can construct a larger size decoder with the help of the smaller size decoder. So first of all, we have to find out that which type of the decoder we have to construct and which type of decoder we are given with. So here are some steps and some examples how this takes place. So the number of lower order decoder for implementing higher order decoders can be find as that how many number of decoders you need. So here is the process. The number of lower order decoder required is equals to M2 upon M1, where M1 is number of output of the lower order decoder and M2 is the number of output of the higher order decoder. So in the same way, if you have to construct a 3:8 decoder with the help of 2:4 decoder. So in this case, M2 is your 8 and M1 is your 4. 2:4 and 3:8. So 8 by 4 equals to 2. So in that case, you require two 2:4 decoder to construct a 3:8 decoder. The same example we are going in the next slide. Suppose we have to design a 3:8 decoder with the help of 2:4 decoder. So first of all, we have to find out the number of decoders required to construct a larger order decoder. So it will be find out with the help of M2 upon M1. Here M2 is 8, M1 is 4. So number of decoder required equals to 8 by 4 equals to 2. And this is the way how these are constructed. So I have two common inputs X and Y, both are common to both decoder because this decoder can take only two inputs at a time because the size of the decoder is 2:4. And I have used the third input as enable, and for the first decoder enable is 0 with the NOT gate, and for the next decoder enable is 1. So here we have used positive logic. That means whenever enable is 0, decoder will work. Decoder will not work. Whenever enable is 1, decoder will work. So these are the three inputs A, B, C. The third input will be the decoder. So I can write A, B, and C. C will be your the MSB of the input line. So whenever enable is 0, the output of the NOT gate will be 1. That means this decoder is active, and according to the input X and Y, there will be the output at the same moment because this enable is 0 and enable is fed to the enable to the 2:4 decoder. That means this decoder will be deactivated. So if this decoder, whenever this decoder is deactivated, we don't care about the input combination, then output will be inactive. That means output will always be 0. So suppose the input combination is 0 0 0. So 0 0 0. So D0 will be 1 and here D0 will D, this is your D0. D0 will be 1, but the case because this enable is 0, that means D4 is 0 and we are getting 1 0 0 0 0 0 0 0, which is desirable. Which is desirable in this case, we have studied here. This is your enable X and Y. So enable is connected to the MSB A. X and Y are the two inputs. Whenever combination is 0 0 0, so enable is 0. Enable is 0, and we should get the output 1 0 0 0 0 0 0 0 like this. So this can be find out here in this case. This is your A, B, and C. So whenever A is 0 0 0, so this decoder will be deactivated and the output of the all four outputs will be 0, and only this decoder will be active and the output will be 1 0 0 0. Suppose the input combination is 1 0 0. So whenever 1 is given, the output of this NOT gate will be 0. That means this decoder will be deactivated and the output will be 0 0 0 0, and it is 100, this is activated, 00 means D4 will be 1. So the output will be 00001000. And we can see the same with the help of the truth table here. When the input is 100, so the output will be 0000, so D0, D1, D2, D3, D4 will be 1000. So this is the way how a lower order decoder can be used to construct a higher order decoders. You can take another example, can try that we have to design a 4:16 decoder with the help of 3:8 decoder. You can try to construct. First, find out the number of decoders. So the number of decoders will be 16 by 8. That is 2. Like this. So here we have taken the inputs as W, X, Y, Z. So W is MSB. It is connected to the enable. For the first enable, it is with the NOT gate. For the second enable, directly. For the first 8 combinations, W will be 0 from 0 to 7. In that case, the first decoder will be activated and it will provide output D0 to D7. And at the same time, the second decoder is inactive. That means D8 to D15, the output will be 0. For the next combinations, 8 combination, when W is 0, sorry, W is 1, then the first decoder will be deactivated and the second decoder will be activated. And in that case, D0 to D7 will be always 0 and D8 to D15 will depend upon the input values X, Y and Z. Now that is a pretty much important topic which we are going to discuss, the function implementation using decoder. And such type of the design is known as ROM, read only memory. You have studied in the computer science or you are studying in the 12 10 plus 2 what RAM and ROM. So ROM is a decoder used to implement a Boolean function, that is the read only memory. And with the help of a decoder, we can implement any Boolean function directly without solving K-map and without requiring any number of gates. So suppose we have to implement a full adder, and when we look into the truth table of the full adder, then sum comes to be, sum is summation 1, 2, 4, 7 and carry is 3, 5, 6, 7. When you look into the truth table of the full adder, then sum will come 1, 2, 4, 7 and carry will come at 3, 5, 6, 7. These are the minterms in the truth table. So we can directly implement these sum and carry with the help of, as input is 3, because it is going up to 8. So for a full adder, input will be 3. So we can use a 3:8 decoder to implement the Boolean function, and the circuit will be like this. We have used a 3:8 line decoder. X, Y, Z. X is the MSB. X, Y, Z are the 3 inputs. Then the operation will be X plus Y plus Z and the output will be sum and the carry. So what we do, we have 8 outputs D0 to D7. Whichever minterms is present in the summation. So in the sum, it has 1, 2, 4, 7. So we use 1, 2, 4 and 7. We take a OR gate and put it as sum. For the carry, it is 3, 5, 6, 7. So we again take a OR gate, 3, 5, 6 and 7, and we add it with the help of the OR gate, because minterms are sum of products and a decoder provides a product terms. When you see here the example, decoder is nothing but it provides product term. So here X, Y, Z is the input. It provides with the 3 inputs, it provides 8 minterms. So in the Boolean function, whichever minterm is 1, that can be added with the help of the OR gates. So we can conclude that here when This total circuit, a decoder followed by OR gate, is known as a ROM, read-only memory. You can try with yourself some example here. Suppose I implement the Boolean function using suitable decoder. We have three inputs. F1 is X, Y, Z. F2 is X, Y, Z again. F3, and for the F1 we have minterm 157. For F2 we have minterm 03. For F3 we have 2, 4, 5. These are the minterms we have to implement with the help of the decoder. So the size of the decoder will depend upon the input. Here we are using three input X, Y, Z. That means the size of the decoder will be 3:8. So all of you please try to do this. Take a 3:8 decoder, mark the inputs as X, Y, Z, marks the output at D0, D1, D2, D3, D4, D5, D6 and D7, and take three different OR gates for each and every output combination. One gate for F1, one gate for F2, one gate for F3, and sum all the minterms, and the circuit will be like this. X, Y, Z input. We may use a enable, or it is not desirable, then we can, if it is not desirable, then we need not to put a line enable. So F1 is 157, so 1 comes from here, 5 is here, and 7 comes from here. 157, that is F1. F2 is 03, so F2 is 03. It may be possible that the many of the minterms you are not using. Here in this case we are not using 6, so it doesn't mean that it will affect the operation of the circuit. Whichever term is not used, you can simply keep it blank, left blank. Now suppose we are giving a Boolean function like this, which is not a standard or canonical form. So what we have to do, we have to convert this Boolean function into the standard canonical form. So we convert first F1 into standard canonical form, as the second term is missing with Y. So we have multiplied with Y plus Y bar. Then the terms come be 057. In the F2, again second term is missing with Y. So we have multiplied with Y plus Y bar, and the minterms comes to be 136. So we can just combine these minterms with the decoder, and the size of the decoder will depend upon the number of inputs. Again here the number of input is 3. That means the size of the decoder will be 3:8. So you can implement it like this. We have used a 3:8 decoder with three inputs X, Y, Z, two outputs F1. F1 is 057, F2 is 136. So this is the way how we construct ROM with the help of decoder and OR gates. Okay, now the next topic is encoders. We'll discuss in the next lecture.